work? Excellent. Well, thanks a lot for having me here. I am equaled up, so we can get started. As said, my name is Bernstein. I'm a faculty member at the University of Zurich, and I want to talk to you today about large graph processing. Large graphs are a topic that is close to my heart. I've been working on them on and off for about 10 years. And I've realized that it's something that is almost ubiquitous. Once you start looking at the world through the graph glasses, they just start appearing everywhere. Let me just give you some examples. So where do we have lots of large graphs? This is example number one. These are cell towers in the, I think this is either Linz or Graz. I always forget which one of those beautiful Austrian cities. The nodes here are cell towers, and the connections here are obviously telephone conversations that are being routed from tower to tower. Phone network. You can have, this is a discussion that's currently a lot happening. It's the smart grid, right? So that's a large graph. You have a power graph. At the moment, nobody in this world can tell me whether for me as a house owner it's worthwhile to put solar panels on my roof or batteries in my cellar, and how I should contribute to this active network once it's coming. This is a large graph, huge problem. Nobody knows really how to manage it efficiently at this point. People are still thinking in terms of big factories, of electricity sources, and lots of small sinks for electricity. That's you and me in our homes. This is the Swiss radioactivity sensor network, just as an example. For other sensor networks, there is lots of sensors around. There are also graphs of information getting exchanged. Lots of the processing needs to happen in the graph, otherwise you can't do it for power reasons, etc. This is the internet, our old favorite graph, probably. This is a beautiful depiction of another graph of a small company in the US. The nodes here are users, and the edges here are friend networks. There is no geographical information in this other than the place where the people live. You can obviously see that some parts of Australia absolutely don't exist for Facebook, and obviously China is absent. Nonetheless, this is another small graph that's very interesting. This is a graph I worked on myself. These are press releases in the second half of 1999, and there is a line between two companies if those two companies were mentioned in a joint press release. And what you clearly can see here, this is the first half of 1999, right? Internet bubble, blue, 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 right? So here you can see Time Warner, they just had bought AOL, IBM, etc. So this is the tech bubble, lots of press releases, another beautiful graph. This is a gene regulatory network, and this is the whole human regulatory network as it's known right now, another beautiful graph. And last but not least, this is the graph I work on and love. This is the graph of open data sets as they're available right now. This is this graph in 2007, and just to kind of walk you through this over the years, it's growing and growing. Those are openly available data sets. Here's the DBpedia, that's kind of information extracted from the Wikipedia, US Census data, lots of other things. If you look at this, and this grows and grows. On the right you see a chart of the number of data sets that participate, and it grows and grows and grows, and it gets more and more. At this point it's about 300 data sets in many sectors, and it has 15 billion edges. A very nice graph, but not the biggest we've worked on. Just think of your standard bank. How many transactions between two accounts are there a day? That's a large graph that's in constant flux. You don't just have accounts, you have people. People have multiple accounts. You have account managers, they manage multiple people, etc., etc. So, I really love large graphs, but I want to process large graphs. And processing large graphs is not that simple. You need to be able to do two things. First, you need to actually be able to process them, to do something with those graphs. And secondly, you need to be able to store them and retrieve them, and in order to run matching queries on them. So let's walk through these two subjects quickly. I can give it 20 minutes. I'll try to stay within those 20 minutes to look at this. So how do we process large graphs? The usual reaction of people when they hear processing large graphs is the following. Well, I'll just put it in a database, and I run some SQL on it. And I'll show you some numbers afterwards. If you put a graph in a database, you're joining the same table with itself over and over and over and over again. My friends at Oracle, even with your biggest system, I will get core dumps. It doesn't work. Idea number 2, I use some custom code or write some MPI stuff. A colleague of mine has worked on porting some graph processing stuff onto the Blue Gene. I don't have a supercomputer at home, and some folks who I met at one of the conferences in Shanghai 2 years ago said they're doing this on the craze, but what you need to get is you need to get a couple of PhDs in computer science, teach them for 3 years how to process graphs, and then you get results. Not an option. Third thing, we use MapReduce, right? You were going to say, MapReduce and HBase. Yeah, but then I need to think how to translate my graph into key value pairs, do my processing, and then translate it back into key value pairs, do some more processing, and then into other key value pairs. You may recall this thing between relational databases and object-oriented programming, and it's not beautiful. So what can we do? We took inspiration from this here. This is people in San Francisco moving about. It's data by Sense Networks, a company that attaches sensors to people and then tries to analyze behavior of large groups of people. And what you can see is those people move around between different places in San Francisco. If you flatten it out and analyze in a graph and do graph clustering, what you can see is that there are actually distinct groups of people within San Francisco that have different interests, but they're actually not necessarily aligned to their geographical layout. If this goes back to the geographical layout of San Francisco, what you will find, it happens in a minute, is that in some neighborhoods there is a lot of intermixing of people, but down here there is none. Okay, the blue people are almost staying here, the dark blue people, the red people are all over town. So if you look at this, just for inspiration for a moment, what you can see is one way to process graphs is actually look at the nodes and the edges, and think of the edges as places where information flows, and the nodes as places where things happen. We took inspiration for that and designed a system called Signal Collect. So think of it as Hadoop for graphs, and I'll explain you the major logic of Signal Collect. So what you have is information is going between edges, and it's being sent along the edges as signals, and then it's being collected at the nodes. Okay? Let's look at an intuitive example. So let's define the graph structure. For example, we take an inheritance hierarchy. We take things like animals, birds, penguins, and owls. Don't worry, I'm not going to tell you about penguins are not flying birds and all these problems that arise from that. And the vertices, so the edges present subclass networks, and what you may want to do is you initialize each of the nodes as the state of the class it represents, and now you want to know about subclassing. A very simple subclassing algorithm is the following. You take this graph and you just send your state along the edges, and then you signal the state along your edges, and then you update the edge with the unit of all the incoming signals, and obviously what happens is you now get a new state, bird and animal, and if you let the algorithm run its cause, eventually what you get is all the subclassing hierarchy. Now this is a very, very simple algorithm, right? We're going to get more complicated a bit. This is a depiction of a run in how it works, right? So at the beginning, the top edges signal, then the next level, and eventually the graph will have reason down. Okay? Now let's do this a little bit more complicated. There are some things you may want to do in addition to just signal along the edges and do things in the edges. You may want to score functions, right? You may want to say in this graph some things are more important than others, and let's do the more important things first than the others. So we have scores to prioritize both the signaling as well as the collecting, so the computing in the nodes. That is one thing we do, and the other thing is we dumped synchronous processing. If you think of Hadoop, it's essentially a synchronous process, right? You map, everybody does his mapping, everybody done now? Okay, we're going to do some sorting. Everybody done with sorting? Fine. Now we're going to do some reducing. And if you use a pig process, you're going to do the same thing over and over again, or in a loop, you're going to circle on this, etc., etc. it turns out there are computations for which synchronous processing is really, really not what you want to do. If you think about it, you have a graph and you have a circle in the processing. What may happen is that your processing starts oscillating around the value it wants to achieve. A very simple depiction in your head is, let's say you want to do graph coloring, and you only look at your neighbors. Oh, none of my neighbors is blue, I'm going to turn into blue. Well, all your neighbors are going to make the same decision. Everybody turns blue. Oh, none of my neighbors is green, so I'll turn into green, right? So actually synchronous processing is really stupid, and it turns out that in graph coloring you converge much slower if you use a synchronous process than when you use an asynchronous process. It's proven that if you do probabilistic reasoning on graphs, and I'll show you that in a minute, you're actually going to oscillate, or there is a high chance that you're going to oscillate in your reasoning, and it's not going to converge. In an asynchronous process, you're going to converge. So you want to be able to do this asynchronously. Let me show you why. Here is another very simple algorithm. It's the single source shortest path. So you want to know how fast is each node in my graph from this node over there. So what we're going to do is we're going to do synchronous processing. So we're going to say messages. When I don't know any better, I'm going to send infinity around. I'm going to update, so collect. It's a very simple collect function. I just update. I'm going to do this again, and again, and again. And eventually I'm going to figure out, okay, I'm done, nothing new is happening, I can be done. Let's add asynchronicity and scoring into this. So we're now only going to signal if the old state is not equal to the new state. And I'm going to do this asynchronously. So we're going to send things out, and now we're going to send some messages out again. And the beauty of this is now I have the 2 here, and you're going to see fewer messages need to be sent around. I'm going to message this here, because I had an update here and an update here, but I'm done. So this may seem longer to you, but it's actually much less messages sent around. And some of the updates happened earlier, and here you could probably even further improve this. Okay, those are very simple algorithms. Let me give you some more complicated ones that you can do. So this is our simple, sorry, this is probably not legible from the back rows. This is our RDF subclass reasoning, so it's a union of all the incoming signals in your current state. This is our single source shortest path. We looked at this before. This is PageRank in 2 lines of code. Actually, it's not code, it's pseudocode. I'll show you in a minute PageRank in 2 lines of code. So you're summing up the, you're collecting is you sum up over your incoming signals. You weight that by 0.85 and you add 0.15 to it. Those were the original parameters in the original paper. Obviously, they're not doing quite that anymore right now. But that is the collect, and the signals you send is the weight of the source state times the source states divided by the sum of weights of all the outgoing edges. Okay? This looks very complicated, but this is actually something called the general sum product algorithm on factor graphs. This is all of probabilistic reasoning on graphs. This looks, it's 4 lines of code, and you can essentially do any kind of belief propagations on graphs. This is very simple, very easy, 4 lines of code. Okay, let's go back to this. I promised you I can do this in 4 lines of code. Here are, 2 lines of code. Here are the 2 lines of PageRank code. Now at this point this is real code, written in Scala. You can see I write the collect function, the 0.15 plus the 0.85, and I fold left over all the signals I get coming in. It's essentially a sum function, and I do the same thing over the add weights. That's PageRank. Now I'm going to add some code to load the graph. I'm just going to show you that. I am running a Sparkle query. Sparkle is a graph query language, which essentially, think of it as SQL without tables, because you're actually just querying the graph, and so you're defining graph patterns. So I'm looking at a edge that is a source and a target, where the source cites the target. So this is a citation database, And then for each of the results, I have a citer and a cited. I add the citer to the graph, I add the cited to the graph, and an edge from the citer to the cited. That's it. PageRank's running. Okay, I'm showing you PageRank running. And what you can see is what's further out is adding first, and then we go inner and inner because there are no updates anymore on the outside. This is just to show you that the scales. This is a speed up by number of worker threads on a multi-core machine. We now have a distributed version running. The graphs are not quite nice because as you distribute over machines, obviously you get the latency between the machines, so the graph looks somewhat like this, where you fall down again on the speed ups. Just to show you that synchronous versus asynchronous is a matter. So this is synchronous, this is asynchronous. You can see it matters on this example, which is PageRank. So we're not the only ones who are doing this, obviously. There's something called GraphLab by some people at CMU. They have a synchronized network. It's much more difficult to build a synchronized distributed system. So we expect them to be more complicated in the scaling part. There's something called Prego that Google announced about the time we announced our system first. It is, again, a synchronous system. They fold the signal and collect into one phase. There is something called HipG, that's by the Free University in Amsterdam. It's a top-down system, a hierarchical system, which does not allow some aggregation of graph edges. And there is something called Parallel BGL, which is the basic graph library just in parallel, so it tries to parallel the basic graph library functions. And then we have our single collect, which you can download right now from Google Code and start playing around with it. I believe the distributed version is online as well. If not, it's going to come by the end of the summer. Okay, now let's talk a little about graph storage. Graph storage is a different problem. With graph storage, you need to think about how do I store large graphs on disk and quickly retrieve patterns from the graph. So one thought you might have is the relational database idea. As I said, bad idea. Another thing is let's just put full text documents online. It's also a very bad idea since you need to actually extract the structure from every document. You may want to think about putting it on HBase. We'll be able to have a wonderful discussion about that later. So how does a graph pattern look like? So this is a possible graph pattern. You have a simple graph of two edges. You bind the first edge. We happen to bind them to URLs. You bind, the first node. You bind the edge to a certain type. And then you want to know what possible nodes can this be, and then you connect it to another node to what possible node can this be, and this edge type is also bound. So in this specific case, I want to know what courses does my colleague Gerrit Weikum up at MPI teach, right? What courses, I don't know, and at what university does he teach those courses. In 2007, we ran an evaluation of how current graph stores do this, and many of them built on top of relational databases. And that was Jenna, that was one of the basic systems. What you see on the x-axis is the size of the data set that we loaded in. This is not a big data set, right? This is megabytes. So we're talking about a data set that is like around 700 megs. And if you look at the milliseconds, this is an abysmal performance. Then we took another system, K-on2, it crashed on us at about a half a gig file size. That was also not very reassuring. Then we took Sesame, that was one of the systems that many people used at the time, which is also not more reassuring. We launched a master's thesis of a student just to write a query optimizer on top of this first system here, and we got this performance here. Well, which one? This performance here. This is just a static query optimizer reading the query, writing the query, and then just running it through the system. So that just tells us how cool and how great we are. That just tells us how abysmal the state of the systems is. Okay? So we decided this is not it. We need to find out how to do this better. So how can you do this better? Well, the first step of what you do, obviously, is you take this query here, for example. We call these things subject, predicate, object. So source, target, and type, the predicate type. the first thing you can do is what Jenna does. It actually has a graph and needs to scan the graph for matches. This is very tedious because you essentially need to transport the graph in and out. That's one option. The other thing that Jenna did, I have to say did at the time, is it takes this first element here and tries to match it into the graph and then does a graph search that's restricted by this element. Actually, these semantics don't give you the full answer set if you do this wrong. Secondly, people throw it into a relational databases and then do self-joins. Bad idea. Then in 2007, there was a Best Paper Award for another paper that proposed the following at VLDB. They said, let's have a table per edge type, and then we can join between different edge types, right? That should be much faster. And they proposed one more difference. Most relational databases are row stores, so they store the row in the leaf of the B plus tree, sorry, for the B tree. These guys say, let's use column stores. Now the advantage is you can use compression. For example, here you can use run length encoding, that's faster. And if you do self-joins, you're not actually reading in the same B tree, but you're reading in two different B trees. So that gave them a reasonable speed up. We proposed something else in 2008 at VLDB, as well as Thomas Neumann and Gerd Weick also proposed something else. They said, well, let's just take each possible permutation and put it in a B tree. So you take the subject, you take the object predicate pair, all possible pairs, and just throw them in a B tree, and just read the B trees in different orders. We proposed something else at the time. Take each pattern, and first of all do dictionary coding on it. Well, that's a no-brainer. Take the long strings and turn them into numbers. And now let's just think that the data structure that answers this query the fastest, and the data structure we could come up with is a hash. So you look it up in the hash, and what you then do is you point the hash points to other hashes, then have the predicates in it. So that's the second element. And then you can go there and look that up. Both of those are order 1 lookups. And then you have an ordered list on the leaves. Why it's an ordered list? Will come up apparent in a sec. So you have a data structure like that, and you can put that data structure efficiently on this. So if you want to resolve your second part of the query, you can now follow these things up in that way, and again do order of 1 lookup. So you can do a bunch of order of 1 lookups and be quite quick in the way you resolve this query. Now why are these ordered lists here at the end? The reason why you get ordered lists here at the end is because what you have here now is a subject predicate object, so a source type target index. What you may want to do if you want to join these things often, you may want to have 6 indices. If you have those 6 indices, what you get is, and I've ordered them specifically in this order here, you may want to join on the bottom ones, and if those are ordered lists, those are sorted merge joins, which are the fastest joins in the world you can think about. Okay, I'm past my time, so I'm going to speed up a bit. What do we have? We have a fast and concise representation. No choices are necessary about what kinds of indices you build, etc. What's negative? Your index can get faster, on average that's actually, larger, on average that's about 3 times, not 5 times in realistic numbers, and updates are expensive. In order to address this issue, we combined a B tree with a hash map. So the hash map points into the leaves of the B tree. So what you get is the order of 1 lookups, but once you do updates, you get fast updates, and you may have to rehash your hash. And during the rehashing your hash, you get a log n lookup and not an order of 1 lookup, so that's slower. We solved this. In the system, we're planning to release such a system by the end of the year, so you can download it and play around with it. I can now show you some experiments as to why we're faster and go through the academic thing of doing this, just to kind of compare. This is a nice query, the second one. If you don't know what your connecting edge is, comparing to the VLDB 2008 example, you see about 1 to 3 orders of magnitude faster than the fastest competing system at the time. Let me jump forward. What we also did in 2008 then So we put this system on an 8 gig iPhone. We put 250 million edge on that first generation iPhone, and just showed that this can be done. Today, obviously, you can put way more edges on such a device. Okay, I need to jump over this as well, since we are out of time. So what do you need if you want to process large graphs? One thing you need is you need to be able to do graph processing, and there are frameworks to actually have graphs or edges in graphs to be first-class citizen. And I would heavily advise you to try and think about these rather than to reinvent them. And then you may want to think about using some systems that are focused on graph processing, such as signal collect, or parallel BGL, the other systems I showed you before. And for storage, you may want to think about using graph stores. I believe our dear friends at Oracle have a RDF option to Oracle available if you want to buy it and test it. I don't know about its scaling, and if I would know, I wouldn't be allowed to tell you, since the Oracle licensing agreement doesn't allow people to publish, what do you call it, performance elaborations. Anyways, I hope that gives you an idea, and if not, drop down to our website, and I will open for questions. Thank you.
Do a full triple store of Hexa store, or implement, because I really like the idea and it seems really fast.
Right. So that's why I say we have our third iteration of implementation, which were all kind of research prototypes that we did for ourselves to actually write papers. And that's why I said we're going to release a version of HexaStore hopefully by the end of the year. Open source, since we want other people to use it and do with it whatever the heck they want to do with it. The clue of RDF Box, which is this third version of HexaStore that we're going to release, is that you can replace the backend with any NoSQL backend that you want to do. We've used Tokyo Cabinet, or whatever it's called. I think it's called Tokyo Cabinet, which is a library of NoSQL indices that is supposed to be faster and better than Berkeley DB for various reasons. It will also allow you to use Tokyo Tyrant, which is essentially a distributed version of those indices. Right? It's Tyrant, you're the tyrant over many machines. We are also planning to have a distributed memory-based backend, and I'm not sure whether it's now going to be MemCache DB or Redis, but it's one of these things. So you'll be able to plug in and out different backends for the different HexaStore indices. So the answer is yes. But we're a mere academic institution that publishes software and throws it over the edge, and hopefully you guys are using it and do things with it.
And the next question would be, plan to do a spin-off?
Do I plan to do a spin-off? At the moment, the simple answer to this would be no. Because it's very difficult to play in this, how do you call it, in this big graph, pardon the expression, and I don't want to be tweeted about this, pissing competition, right? There is this kind of, there are these companies out there that say, oh, we can do 15 billion, oh, we can do 100 billion, and we can do 50 million billion. And if you want to play this game, all you need is lots of engineers. There are some commercial systems out there. Maybe one or two of the students are going to decide to start a consulting company out of there. You know, I think eventually the Oracles of the world are going to pick this up, and they're going to buy either one of the commercial providers, or they're going to buy one of the open source systems that's out there, and the game is over. HP tried this, by the way. Jenna was an HP project. HP failed. They decided not to commercialize it, but to actually donate it to Apache. And Jenna is now an Apache project, and there are some triple stores for a part of Jenna that are faster than the old ones we tested in 2007. So you can look at that. I believe they have TDB, and they also have a clustered version. I don't recall what it's called. But spinning off companies causes a lot of gray hair. And you need to decide when you want to get what gray hair and in what market you want to play. Who here has gray hair? Are you spinning off the company?
Oh,
soon!
Yeah,
soon. Any other questions? Yeah?
So your signal collect framework, basically you're saying that can you guarantee the correctness of any algorithm if you just do it async instead of sync?
No, you can't.
Yeah, so you're trading something over there.
So that is what the people at CMU try to do. The CMU guys try to give you correctness guarantee. The problem if you try to do this with correctness guarantees, you need to lock your neighboring edges. And locking means, in a distributed setting, means time, complexity, and headache. The beauty of the algorithms we have been looking at, which are, you know, kind of distributed probabilistic reasoning, is you don't care. Because it's going to even out eventually, right? It's those. Okay, so let me put it that way. Many things that you use on a daily basis are actually graph reasoning, probabilistic reasoning algorithms. Actually, PageRank is a special form of a Markov random field, which is one of those algorithms. It's a very special, simplified, dumbed-down version of such an algorithm. PageRank works beautifully without these correctness guarantees. It will just eventually converge. So you need to worry whether the asynchronous version does converge, will do your things, but the beauty of MRFs is they do converge. Most of the belief propagation algorithms do converge under these settings, but there can be algorithms that do not converge where you lose this, especially if certain nodes don't wake up or die of starvation, so you need to be careful about that. So it comes with another set of problems, but you can also always fall back to our synchronous version. I cannot give you those guarantees. If you want to use that, use GraphLab by the CMU guys. Have fun.
One more please. You said that you can destroy, so for the second part for the storage, when you use your hash table, no? And then you say that an update can cause problems, and then you use a B-tree to make sure that the updates, after the updates it stays consistent, can you still guarantee a constant lookup time?
Okay, so when we started with this, we were assuming that you mostly read, which is actually true for many graphs. And once they're loaded, you have very few updates. I say for many graphs, not for all. I can give you a bunch of scenarios where that's not true. It turns out that the Sparkle standard 1.0 didn't even have an update statement. Sparkle 1.1 has an update statement. And so for the longest time, people were really not worried about updates. Updates do happen, in the real world especially. So what we did is, obviously, eventually hashes will get collisions, and you may have to rehash. Rehash will take a lot of time, and so you cannot guarantee order of one lookups. So what we thought is, in those cases, you may want to fall back and you say, okay, I'm happy with a system that gives me order of one lookups most of the time, and whenever it's rehashing, it will give me order of log n lookups. Again, log n sounds very, very short unless you have a large key space. And the difference between the relational setting and the graph setting is that you only have one key space for all the nodes, right? In a relational setting, you're dividing your world into multiple tables, so log n doesn't grow too much. But in this world, you have one key space, so your key space grows and grows, and log n can become very, very slow eventually. So all we can do is we can say, whilst we're using one of our cores to rehash, your other core is going to provide you with log n. But during that time, we're in log n space. I cannot do magic. If I could do magic, then I would have a spin-off company. No, I wouldn't have a spin-off company. I would be knowing what the IBM stock price in 2 weeks is, or the Oracle stock price in 2 weeks is, and I would be a billionaire. I wouldn't be standing here. I would be on my yacht in Saint-Tropez. I'm not.
Not yet.
Not yet. Thank you. Thank you. Any more questions? I'll be available afterwards, and I'm sorry for taking too much time.